Okay, so we return to the three-part lecture series on the limbic system, and this is the third part of the set presentation. We'll be talking about the last parts mentioned in your textbook Guyton, the hippocampus, and the amygdala. Their locations we have already pointed out, but just to refresh your memory, let me just take you there to the anatomy. So here we see the hippocampus and the amygdala. Okay, this is the hippocampus here, and it loops right here, and this swollen end, it's the amygdala. Another angle to this is this. As you can see, this is the this is the amygdala here. Let me just use a pointer. So this here is the amygdala, right? And this is the hippocampus. We will discuss. We mentioned that they are part of the limbic system, very important parts, and we will discuss it. What does that mean? Go on to the relevant slides. Yes. We'll start off with hippocampus. So, what is the hippocampus? Anatomically, we've mentioned it. It's a very important part of the limbic system. Not shown in those diagrams, it has extensive linkages to the cerebral cortex, the other components of the limbic system. So it's a very busy place in terms of its inputs and its outputs. Inputs, again, as I mentioned, from the cerebral cortex and other components of the limbic system, and then it sorts of dishes out its product. We'll talk about its quote unquote product back to the different parts of the limbic system. Point to note about this is all of the sensory information coming up the ascending tracts and going towards the cerebral cortex, passing through the brainstem, of course, then passing through the midbrain, and then on relaying through the thalamus into the cerebral cortex. So right at this moment now, you need to add to that knowledge of yours of sensory physiology, is that at the level of the brainstem, there are collaterals of all the sensory information coming up. At this point, where it's passing through the brainstem, it gives collaterals to the limbic system. You can say that a copy of all of the sensory information that is destined for the thalamus and then on to the cerebral cortex, a copy of it is given off at the level of brainstem while the sensory information is still ascending. This copy is received by, guess who? The hippocampus. So almost any type of sensory experience that you experience uh, stimulates some part of the hippocampus because a copy of it is given off to the limbic system. And hippocampus is that let's say not the postman, the mailbox of this information, and it has areas which are still not very fully understood. It's indeed a mysterious little place inside a mysterious box called the limbic system. Okay. And when it is stimulated, it in turn then distributes the information to the anterior thalamus, the hypothalamus, and other parts of the limbic system, as I mentioned earlier. So, what's this copy, the copy of the sending sensory information coming to the hippocampus? What's the point here? I mean, let's take the example of pain. Pain is a sensory modality, a sensory information that is sensed by a peripheral receptor. It then is transmitted to the spinal cord, where it's taken up the spinal cord, passes through the brainstem, relays through the thalamus, and the sharp variety of pain is relayed further to the cerebral cortex, while the chronic uh, pain, which doesn't need a very sharp localization, very acute localization, terminates in the thalamus. Now that I'm saying that a copy of this, all the stuff is given to hippocampus, a copy of this pain is also given to the hippocampus. This is the important point now to remember. So, what's the point? The point of sending information, sensory information, up to the thalamus and to the cerebral cortex, specifically the cerebral cortex, is to get the CNS to respond to this pain. So, if you have just put your foot on something hot, you want the brain to trigger certain appropriate motor movements, which should remove this foot off the hot area, right? That's the motor output. Where does hippocampus and limbic system come in? So now just think about a painful experience. And no, not this lecture. This lecture is not painful. Even if it is, it doesn't count. That's a joke. Okay, coming back. So again, the hot stuff that you stepped on, you put your foot on this hot object, it also will change your mood, wouldn't it? I mean, you won't be happy about it or excited. If you are, you should immediately go to the nearest doctor. Okay, so you won't be happy. Your mood will change. You'll be shocked, annoyed, uh, and later on a bit sad that you sort of burned the sole of the foot. So this emotional aspect of pain, the affective with an A, the affective uh, response, in addition to the motor response, this affective response, this behavior-related response, is what the hippocampus adds to the response of the CNS to pain and to every other modality of sensory information. Um, Here, let me just connect a previous concept that we were discussing of reward and punishment. So the hippocampus would not respond to sensory information which does not trigger any reward or punishment center. So again, putting on that shirt without the B in it will not uh, cause any sort of behavioral response from you, the organism. However, if there was a bee in it, which eventually, unfortunately, stung you, then there will be, every time you put on a shirt, maybe that particular color of shirt or the smell of the shirt or the grease, your brain will go to some interesting details to link or to tag cues related to this experience of the bee stinging you and this shirt being caught in the middle, right, of this whole scenario. And it will be careful next time. So this is the behavioral element of of this whole experience. So hippocampus gets turned on by incoming sensory information, uh, which will trigger a reward or a punishment center. The rest of the stuff, although it is forwarded to the hippocampus, just like the other areas of the cortex, cerebral cortex, and thalamus, but it's rejected. It's not processed. No output is given, neither by the cortex or thalamus, nor by the hippocampus. This should be very very clear. That for the hippocampus to be interested in responding uh, by altering your behavior to certain sensory information, it needs to have triggered some reward or punishment center. And then the second component is then memory formation also is triggered when hippocampus is triggered. So this is what we mean by incoming sensory signals can initiate behavioral reactions. Right. Um, one other bit is that hippocampus has is rather notorious for epilepsy. So it's the circuits of hippocampus are arranged in a way that they are reverberatory. So once you send in an action potential into the hippocampus, don't expect it to just be uh, one action potential and it will just go stimulate one area and then stop. No, that's not how it is. It has various reverberatory circuits that you have studied in your sensory physiology. So once these circuits are triggered, they will go round and round and round. Now remember, and if you can connect now with the reward and the punishment center discussion and memory formation, when we discussed memory formation in the last part of the second part of this lecture series, we mentioned rehearsal or reinforcement. Now, what is the physical electrical phenomena underlying this reinforcement? It's the repetition of this incoming sensory stimulus. So what hippocampus does is it's like a how do you say this? It's like a photocopying machine. It takes the original signal, rehearses it, or not photocopy, rehearses it so much. It's like a parrot sitting in there. It will rehearse and rehearse and rehearse and rehearse. Remember, only the one, only those information that either goes towards a reward or punishment, only that. It will rehearse and rehearse and rehearse so that eventually it becomes a memory. Okay? This is something very important. Uh, but at the same time, this rehearsal stuff, these reverberatory circuits, uh, make it prone to, ironically, to epilepsy. So hippocampal epilepsy is common and one of the commonest forms of epilepsy. It also maybe it's postulated that it's maybe due to the fact that it does not have the full six layers cortex in it. It only has three. Okay? So the rest of your cerebral cortex and the cerebral structures have six layers. Uh, However, the hippocampus has three. This is an important point to note. Right. So we come to the last part, which is the function of the hippocampus. We have uh, uh, almost mentioned all of the stuff that hippocampus does in the last part of the previous discussion. And this slide, just cap it up, is that its role in memory, its role in learning, is basically um, the things that it does to form memories. Okay, when you learn, you form memories, right? So hippocampus is known for memory formation. I just described it, how it does it. And through this, you learn. You remember things, new things, and you learn. Now, in the previous unit, cerebral cortex, uh, you must have seen one of my slides regarding memory. And I mentioned various classification of memory. The basic Guyton classification is short-term, medium-term, and long-term memories, right? There's another classification that I mentioned, that's from Guyton. It's declarative versus skill-based memory. Declarative learning is all the semantic memory, all the terms that you remember, the names, uh, theoretical stuff. Okay, while the skill-based, as the name indicates, is a skill that you've learned. Okay, now hang on. Uh, Look at this line here. Declarative memories require hippocampus. So, if we were to, Allah forbid, remove the hippocampus or damage it somehow or major chunks of it somehow, what will happen? What will happen is amnesia. you will forget some stuff. But there's an interesting pattern here. The memories that have already, and listen carefully, the memories that have already been stored in the memory storage area, which hippocampus is one of those areas, and there are other cortical areas which store memories. Old memories, already established memories, will remain intact. Very important point. But new declarative memories will not be formed or will be very much affected. So you won't be able to remember people's names or remember concepts, uh, remember telephone numbers, addresses, so on and so forth. I mean, it's not a fun life. Um, what you may remember is maybe having a transaction with someone, a verbal little talk or interaction with someone, which spanned a couple of seconds, but then you'll forget it. So that's how it is. It's not mentioned here. It's called anterograde amnesia. Anterograde amnesia is when you retain your old memories, but what is affected is the formation of new memories. That's anterograde amnesia, as opposed to retrograde amnesia, in which the previous memories are also affected. Right. That's what you need to know about the hippocampus. Give it a good reading again from Guyton. Moving on to the last part of this presentation is amygdala. Keep a mental picture of where the amygdala is, and then check this out. So it's literally the end of the hippocampus, right? And if you have appreciated what the hippocampus does, you will appreciate the location of amygdala. So it's like they have Guyton very poetically describes it as the window or window through which the limbic system sees the place of the person in the world. So very poetic way of describing it. It's like a compass. It's like the North Star of the limbic system. Okay? Things that come into the limbic system to the hippocampus pass through the amygdala, basically. Okay? And amygdala, again, a lot of it is mysterious, but it seems to contribute to a whole lot of function. I'm tempted to say that it mimics hypothalamus itself, if I may say so, and you will see how it does it. So its connections, again, it has extensive connections uh, from different parts of the limbic system itself, but also the, from the other parts of the CNS, in these temporal, parietal, and occipital lobe. Um, then there's the output. The efferent fibers then go to the same cortical areas, the same hippocampal and thalamic and hypothalamic areas. So it's again just like the hippocampus, uh, but more in terms of busyness and connections. These are the vegetative functions of amygdala. You can see that just like the hypothalamus, it it seems to be involved in a lot of vegetative functions. And it's indeed mediated in collaboration with hypothalamus. Then you have some motor actions. They are peculiar, and this forms a part of a very interesting syndrome, which we will end this whole lecture series at, the Klüver-Bucy syndrome. But stimulation of the amygdala leads to some interesting uh, movements of the animal and on which this experiment is taking place. Uh, this is interesting. The various movements of olfaction and eating, licking, chewing, and swallowing. So basically, I missed out a little piece of information regarding hippocampus and amygdala. Basically, they are uh, very much linked from an embryological point of view with the olfactory. system, the olfactory area. That's why you see that, and it's very evident in animals, that they tend to sniff things. Like you must have seen a cat or a dog, uh, and many animals. They, especially the mammals, they basically sniff stuff, and the sniffing determines some very important things. So, for example, food they will sniff. They will sniff what sort of food it is, and by sniffing, and its olfaction is very much developed, much more developed than it's developed in us, in the lower vertebrates. The sniffing, the smelling, olfaction will determine whether the animal will eat this or not. Then there are scents given off by the opposite gender in mating rituals. Again, smell will determine whether this organism will now mate or not, and even danger can be smelled, quote unquote, uh, by the animal uh, in various scenarios. So, literally, life and death depends on olfaction in lower vertebrates. So, hippocampus uh, has a close association with olfactory areas embryologically, and so does amygdala, right? And hence, you see there's a lot of olfaction and eating related movements when you stimulate the amygdala. But once again, just a quick going back to the hippocampus and olfaction, we tend to remember smells, both the pungent because they stimulate the punishment areas, yes, and the good ones because they stimulate the reward centers. There you go. Learned an additional thing here about the hippocampus. Coming back to amygdala, so we've done this. Now the behavioral stuff. Now you will see all sorts of crazy things here. Okay, and it is crazy. And we are now running up to the even crazier syndrome, the Klüver-Bucy syndrome. But for now, let's see that stimulation of certain areas. It's the whole plate here. Look at it. Rage, escape, punishment, severe pain, fear, everything which is, well, not so nice. So the whole spectrum of things which you would like to avoid, these sort of behaviors. However, stimulation of other parts can lead to pleasure and reward. So this here is a complete palette here, right here, of behavior. Then there are, if this was left out, sexual activities. Again, you can see a whole array of sexual activities when you stimulate the amygdala. So once again, recapping it, uh, functions mediated by the hypothalamus, involuntary movements, special mention, olfaction, behavioral functions. So you can expect a small or a part SEQ in your exams on functions of amygdala, or a more fuller SEQ on functions of hippocampus and amygdala. Finally, the Klüver-Bucy syndrome. This is a syndrome in which basically how did it come about? Uh, in the initial years or initial centuries, way back when we didn't have much information about the limbic system of the brain, epilepsy would be treated by removing chunks of the brain. It would be a hit and trial method, but they found that if you remove again the part of the hippocampus or amygdala, you would treat, quote unquote, treat the epilepsy. You did treat the epilepsy, however, there was a huge price to pay for it, called the Klüver-Bucy syndrome, in which this person now, well, almost becomes a childlike animal, if you want to remember it like that. A childlike animal. This person would be fearless, extremely curious about everything and everyone, uh, would be very unsocial, by the way, would say enter a social place with lots of other people, and start behaving in a way which is very inappropriate. Uh, Again, this is a childlike behavior, and the sexual activities are also unnatural and unsocial. So, removal of temporal lobes and amygdala leads to Klüver-Bucy syndrome. This would be it. References are Guyton, the chapter on limbic system, and Rhodes Physiology, which is a wonderful book, clinically oriented physiology. Thank you.